And then number 2, we will discuss the inverse of a 2 by 2 matrix. That is what we are discussing in our lesson today. So feel welcomed, students, and let's discuss in details what these two subtopics have to do. Before we discuss the determinant of our 2 by 2 matrix, students, we need to understand one thing, that when talking about a matrix is singular. When there are more than one, we talk of matrices. And a matrix is simply the arrangement of elements in rows and columns. The arrangement of elements in rows and columns. For instance, if I have this as my matrix M, A, B, C, D are what you're calling elements. They are simply the characters of this matrix. And these elements have been arranged in what we call rows and columns. What do we mean by rows? We mean the horizontal arrangement of elements. The horizontal arrangement of elements is what you're calling rows. So these are the rows of the matrix. Elements A, B are in the first row, C, D are in the second row. When we look at the arrangement vertically, and then we talk about what we call columns. Columns. So columns is simply the vertical arrangement of elements. That is what we call the columns. And the rows are horizontal. Again, for example, we could have an example of a matrix 8, 6, 2, 7. These are elements. 8, 6, 2, and 7 are elements of the matrix. And they have been arranged in rows and columns. When talking of rows, we're talking about the horizontal arrangement. And then column, we are talking about the vertical arrangement. That is what we mean by a matrix. Number 2, students will need also to understand that in a matrix, elements are believed to be in diagonals. So A, B, C, D, we can also explain the arrangement of elements in a matrix to be in diagonal form. What do we mean by diagonal arrangement? This element A and B happen to be in diagonal form. If, for example, illustrate this using a rectangle is a quadrilateral. A quadrilateral meaning it has 4 sides. The endpoints, the vertices of this rectangle, when joined, we obtain what we call a diagonal. Therefore, AC is a diagonal. AC is a diagonal. When we join B and D as well, B and D, again, this is a diagonal. That is in quadrilateral. But for our case in matrices, the element A and D are in the diagonal form. Equally, element B and C are as well in the diagonal form. So how do we refer to these diagonals in a matrices? In matrices, this diagonal, the one running from the left to the right, is what we call the main or the leading diagonal. The main or the leading diagonal. And the other diagonal, this one, is referred to as the other diagonal. So do not ask us what is the name of the other diagonal. It is just referred to as the other diagonal. Therefore, matrices also constitutes of elements arranged in diagonals. And we have 2 diagonals, the leading diagonal and the other diagonal. Why do we need to know about the diagonals? It is important to know because the understanding of our first element the determinant of a matrix is based on how to identify the diagonals of matrices. And we are specific that we are going to do matrices that are of order 2 by 2. Again, students, do you understand what we mean by the order of a matrix? The order of a matrix, we're talking about order of a matrix. Order of a matrix. We are simply looking at the number of rows. The number of rows against the number of columns. The number of rows against the number of columns. Number of rows against the number of columns. You look at the number of rows against the number of columns. So that is what we discuss under the order of a matrix. And therefore, if you have a matrix that has 2 rows and 2 columns, then we refer to that as a matrix of order 2 by 2. And those are the matrices that we will be discussing in our lesson today. That the ones that have 2 rows and 2 columns. For instance, this matrix here, 8, 6, 2, 7. We have 1, 2 rows, 1, 2 columns. That is what we'll be discussing today. So therefore, what is the determinant of a matrix? What do we mean by determinant? Determinant of a matrix. And in this case, our focus is 2 by 2 matrix. Yes, the determinant is simply, this is simply the difference in the product of elements in the leading diagonal and the product of elements in the other diagonal. What we mean by this is that we are going to obtain the product of elements in the leading diagonal and get the product of elements in the other diagonal, then get the difference. Because of the difference, we'll subtract. So this is what we are illustrating. A, B, C, D is our matrix. So what is the elements in the leading diagonal? It is A and D. Therefore, when talking of determinant, we say it is A times D minus B times C. Minus B times C. So A times D, that gives us AD minus BC. Minus BC. This is our determinant for this matrix. The determinant will be AD minus BC. So if you are given a question to determine the determinant of a matrix, then what you shall only need to do is to multiply the elements in the leading diagonal and then multiply the elements in the other diagonal, get the difference. You will be able to obtain the determinant. So let's look at examples, students. Let's look at the explanation we've done using examples. We are told, number 1, given that M is negative 2, 1, 6, 5, find the determinant. Find the determinant of M. Find the determinant of M. That our matrix M has the elements negative 2, 1, 6, and 5, and we are required to find the determinant of M. From the explanation, students, how will we work it out? Yes, the elements in the leading diagonal is -2 and 5. The other diagonal has 1 and 6. Therefore, our determinant will be -2 times 5 minus 6 times 1. -2 times 5 minus 6 times 1. -2 times 5 gives us -10 minus 6 times 1 gives us 6. And this gives us -16 as our determinant. So the determinant of this matrix is -16. Again, why -16? That is the difference between the product of elements in the leading diagonal and the product of elements in the other diagonal. We will look at the second example. The second example, we are told to determine the determinants of each of the given matrices below. We determine the determinant of each of the given matrices below. We have our first matrix is 4, -6, 3, 10. And then we will look at the second one, where we have 1/3, 2/5, 6, 1/7. Those are the matrices that we have. We have 4, -6, 3, 10. And then we have a third, 2/5, 6, and 1/7. Let's start with the first one, students. What are the elements in the leading diagonal? The leading diagonal has 4 and 10, and the other diagonal has -6 and 3. Therefore, to work out the determinant, we will take 4 times 10, the leading diagonal, minus -6 times 3, minus -6 times 3. 4 times 10 gives us 40, minus 6 times 3 gives us -18. And this gives us a total of 58, because minus is plus. So the determinant is 58. Number B, not only will you have matrices given as whole numbers, but we may have matrices that are constituted by elements which are decimals or which are fractions. So in this case, we have fractions. We will work out the same way, that the determinant of this matrix, will be equal to 1/3 times 1/7. Then we minus 2/5 times 6. 1/3 by 1/7, that is 1/21. We minus 2/5 by 6 is 12/5. So we get this, the LCM of 21 and 5, that is 105. 21 into 105 is 5 times, less 5 into 105 is 21. So 21 multiplied by 12, that is 412, 252. 252 as the product. Then we less this, you get it is -247/105. We will not give it as -247/105 because 247 is larger than 105. So as a mixed fraction, it will be negative 2, that is 210, then 37 over 105. That is our determinant. So students get to know that not only will we deal with whole numbers, but we will get to a point of dealing with fractions or decimals. Good. That is what students need to understand in the case for the determinant of a 2 by 2 matrix. But to make an extension to that, students need to understand there is something we call a singular matrix. A singular matrix. So what is a singular matrix? What is a singular matrix? Yes, a singular matrix is simply a matrix whose determinant is 0. This is simply a matrix whose determinant is 0. A matrix whose determinant is 0. Meaning, if you work out determinant in the way we've done in our examples, and you obtain the determinant to be 0, then that is what we call a singular matrix. For example, if you have a matrix like 4, 4, and then we have 16, 1, this matrix will be singular. Why will it be singular? If you take the product of elements, the leading diagonal, it will be 4 by 4 minus 1 by 16. So this is 16 less 16 is 0. This matrix becomes singular. But in most cases, questions on singular matrices will not really be as such, but we shall have to determine the values for the unknowns in a matrix. And so once the statement singular matrix is mentioned, students, then be able to know that singular matrices refers to those matrices whose determinant is 0. And in most of the examples we shall be doing, we'll be finding a situation where we have to obtain a quadratic equation and solve the quadratic equation using the methods we've been able to know, and then we obtain the value for the unknown. An example to this effect, number 1, you're told, find the value of x in m equal to x minus 4, 3, 4, 10, given that m is a singular matrix. Given that m is a singular matrix, we determine the value of x in the matrix M, whose elements are x less 4, 3, 4, and 10. And the instructions is that M is a singular matrix. The word singular should not make you run away from this example. We've already explained what singular matrix is. The determinant is 0. Therefore, what you only need to know is how do you get the determinant? You get the product of elements in the leading diagonal minus the products of elements in the other diagonal. So we shall have 10 into x less 4 minus 3 times 4. 3 times 4. So that will mean this is equals to 0 because it's a singular matrix. By expansion, this will be 10x less 40 less 12 is 0. Minus 40 minus 12 is minus 52. Therefore, this is 10x minus 52 is 0. We collect like terms by taking negative 52 to the right side, turns positive. So 10x equal to 52. Then we divide by 10, divide by 10, this cancel out, and x is equals to 5.2. That is the value of x in that matrix. If that is not the case, then we will have such a structure that not told you find the value of the unknown in the matrix A equal to with x 9 3 2x x 9 3 2x given that A is a singular matrix, x is a singular, this is 3, given that x is a singular matrix, we find the value of the unknown, and our known in this case is x. So where do we start, students? We start with the fact that we are talking of singular matrices whose determinant is 0. So what will be our determinant? Our determinant will be equal to 3x times x minus 3 times 9, and this will be equal to 0. 3x times x, 3x squared minus 27 is equals to 0. We take negative to the right side, so 3x squared is equals to 27. Then we divide by 3, this cancel out, x squared is equals to 9. And so what is our x? Plus or minus the square root of 9, which is 3. So our values of x is either positive 3 or negative 3. That is to imply that you will either have a situation where you have the linear equation, or you'll end up with a quadratic equation. Be able to know how to work it out. At the end of it all, the main thing is based on understanding how to determine the determinant of a matrix, which is simply the product of elements in the leading diagonal minus the products of elements in the other diagonal. And number 2, to understand the concept singular matrices, that they are matrices whose determinant is 0. Good. That is our first area that we were to discuss, discussing determinant of a 2 by 2 matrix. Progressively, once you've been able to understand the concept of determinant of matrices, students need also to understand what we call the inverse of a 2 by 2 matrix. The inverse of a 2 by 2 matrix. We're talking about the inverse, we are reversing something, but in terms of matrices, what do you need to do for you to obtain the inverse of a matrix? I'll give you the highlights of the procedure that is undertaken here. Number 1, student must be able to know how to get the determinant. So you determine the determinant. You determine the determinant of the matrix. Once you obtain the determinant of the matrix, step number 2, you interchange elements in the leading diagonal. You interchange the elements in the leading diagonal, meaning you shift the position from one position to the other, as well do the other case. And then number 3, you reverse the signs of elements in the other diagonal. Reversing the signs, if the element had a negative sign, it turns to positive. If it had a positive sign, it turns to negative. That is number 3. And then After you've reversed the sign and you've interchanged the elements, you obtain a new matrix. So the last step that you do, you simply multiply 1 over the determinant, by the resulting matrix, So those are the 4 steps that students will need to know. That if you are given a question to get the inverse of a matrix, step number 1, be able to obtain the determinant of that matrix. Number 2, you interchange the elements, the leading diagonal. Number 3, you reverse the signs of elements in the other diagonal, and then you multiply 1 over determinant by the resulting matrix. To illustrate this using a general case, students can be able to look at this case here. We have a matrix, for example, A, B, C, D. These are matrix, a general matrix. To follow these steps, we've said the determinant is equals to AD less BC. That is the determinant of that matrix. Number 2, you interchange the elements in the leading diagonal. So you shift. Where there is D, you shift to this position. A, shift to this position. So you'll have D, A. And then change the signs. Negative B, negative C. So this is what you are calling the resulting matrix, of which you will now multiply by 1 over AD less BC. You will now be able to obtain the inverse of a 2 by 2 matrix. It's a very simple step that you need to follow to get to the inverse. So students, having explained this, let's look at these examples together and see how practically can you be able to obtain the inverse. Given that A is equals to 1, 4, 9, negative 6, find. And again, students, be very careful. They will not write too much. They will just write A raised to power negative 1. That is the implication that you are supposed to get the inverse. If they don't put it in words, they will write it in simple that way. It means the inverse of A. Therefore, let's start off 1, 4, 9, and negative 6. Our determinant will be equal to 1 times negative 6 minus 9 times 4. So this is negative 6 less 36, negative 42. Then number 2, let's interchange these elements. So we have negative 6, 1, and then change the signs, negative 4, negative 9, and multiply by 1 over 42. This is negative. So this will give us 1 over 7, 2 over 21, we have 9 over 42, then negative 1 over 42. If someone is lost, students, this is what we've done. Negative 1 over 42 times 6 gives us positive 6 over 42. And 6 can be divided, 42 can be divided by 6 to have 7. So that's why we have 1 over 7. 1 over 42 times negative 4 will have positive 4 over 42. 2 is 2, 2 is 21. That's why we have 2 over 21. Then negative 1 over 42 times negative 9 is positive 9 over 42. Again, that can be simplified because 3 can divide 3. 3 is 1 into 12, 4. So that should be 3 over 14. To simplify, it should be 3 over 14. And then 1 over 42 times 1, that gives us negative 1 over 42. And this is the inverse of our matrix. So we look at the inverse in that way. Either they will write the word inverse or they will write a power negative 1, be able to obtain that. And now, students, I want to bring in a broader question that encompasses various aspects that we've been able to look at. And this will be the case that given that X is a matrix 2, negative 1, 4, 9, Y is the matrix 1, 2, 10, negative 8. Find A, Y such that, so this is Z, sorry, Z such that Z is equals to 2X plus Y. Part B, will now have to get the determinant of Z, and C the inverse of Z. Those are three matrices, and I've put it that way so that we're able now to move in this line. How do we determine the determinant of unknown matrix? By first following up the steps that you've been given from the given matrices. So where do we start, students? We have X 2, 4, negative 1, 9, and we have Y 1, 10, 2, negative 8. The instruction is that Z is 2X plus Y. So we'll start from that point and say our Z will be equal to 2 into X. X is 2, negative 1, 4, 9, plus Y, which is 1, 2, 10, negative 8. Now we expand. Multiply what is outside the bracket by every element in the bracket. And so that will be 2 by 2 is 4, 2 by negative 1 is negative 2, 2 by 4 is 8, 2 by 9 is 18. Then we add 1, 2, 10, and negative 8. We add elements in their respective position from each matrix, meaning first element in the first matrix, first element in the second matrix. So 4 plus 1 is 5. Negative 2 plus 2 is 0. 8 plus 10 is 18, and 18 plus minus 8 is 10. That is our matrix Z. Therefore, in the question, anywhere they are mentioning matrix Z, the matrix Z is 5, 0, 18, 10. So we need to use this matrix Z to work out part B, where the instructions to get the determinant of Z, and part C, the inverse of Z. So what do we do in this case? Very simple. Take our matrix for part B. Z is 5, 10, 0, 8, 10. We get the determinant, and the determinant is equals to 5 times 10. We minus 10 times 0. 5 times 10 gives us 50, less 0. So the determinant is 50. Our determinant is 50. What about the inverse? Inverse of Z, which will be written as Z power negative 1. We've said in the inverse, get the determinant. So we already have the determinant. We reverse the elements. So we shall have 10 taking the position of 5 and 5 taking the position of 10. And then have this change in signs. So this will be 0, negative 10. And then we multiply by 1 over 50, which is our determinant. We expand, therefore. 1 over 50 by 10 gives us 1 over 5. 1 over 50 by 0 is 0. 1 over 50 by negative 10, negative 1 over 5. And 1 over 5 by 5 is 1 over 10. That is our inverse. So that is how we obtain the inverse of a 2 by 2 matrix for this case, for the matrix Z and A that we've worked out with. Again, students, I will take you back to where we mentioned the word singular matrix and add something to that statement. We've said singular matrix. When you're explaining singular matrix after discussing the concept of determinant, we purely say that a singular matrix is a matrix whose determinant is 0. After you've now gone through the inverse, we add in a statement that singular matrices have no inverse. So if you are told a statement that you find the value of the unknown in a matrix that has no inverse, then know that is a singular matrix. So we are adding something here that it's a matrix. It is a matrix that has no inverse. And remember, the determinant is 0. That is what we call a singular matrix. So given that statement, we can therefore work out number 3. Given that statement, we can work out number 3. And this is our question 3. Find the value of A such that the given matrix is this given matrix such that the given matrix has no inverse. Given that this given matrix has no inverse. So you have 2A plus 4, then we have 8, 3, and negative 2. We find the value of A such that the given matrix has no inverse. Again, I'm repeating, they might not mention that it's a singular matrix, but rather say that matrix is or has no inverse. Then remember, any matrix that has no inverse is a singular matrix. And therefore, if it's a singular matrix, the determinant is equals to 0. So we simply work out with figures, and we work it out this way. What are the elements in the leading diagonal? We have 2A plus 4 and negative 2. The elements in the other diagonal is 3 and 8. Therefore, our determinant, as explained before, will be negative 2 into 2A plus 4 minus 3 times 8. And because this matrix has no inverse, then this determinant will be equal to 0. So we expand, this will be negative 4A, negative 8 minus 24 is equals to 0. Minus 8 minus 24, that is minus 32. Therefore, minus 4A minus 32 is 0. Take this to the right side. Minus 4A is equals to 32. Then divide by negative 4. Divide by negative 4. This cancel out. And A is equals to negative 8. So it means the value of A in that matrix, for that matrix to be singular or to have no inverse, is negative 8. That is our question 3. And our last example on this case, our last example is number 4. The following matrices have no inverse. Find the value of the unknowns. Find the values of the unknowns. Find the values of the unknowns. The first matrix that we are having is a matrix X plus 2. Then we have 5, 2. And then we have this as 7. That is the first matrix. Now the matrix x plus 2, 5, 2, 7 has no inverse. Again, has no inverse is what guides us. This statement, it has no inverse. It means that this matrix has a determinant of 0. So students, let's do the multiplication. 7 into x plus 2 minus 10 is equals to 0. Minus 10 is equals to 0. So this gives us 7x plus 14 minus 10 is equals to 0. 14 minus 10 is 4. Is equals to 0. Then take this to the right side. 7x is equals to minus 4. Over 7. Over 7. This cancels. So x is equals to minus 4 over 7. And if you replace minus 4 over 7, you will try to work it out. You will still find the determinant of this matrix to be 0. So that is the first case where we are determining the value of x for which this matrix is equals to, has a determinant of 0. Let's look at the second one. Now we have the case for y plus 2. Let's use negative y minus 4, and then we have 3 with negative 2, and then we have 2 at this point. So we get the value for y. The determinant again, students, will be leading diagonal 2 into y minus 4, then minus 2 times 3, and equate that one to 0. By expansion, this is 2y. 2 by 4, it's 8, minus 2 by 3, minus 6, and equate this to 0. Minus is plus. So we have minus 8 plus 6, that's minus 2. Therefore, 2y minus 2 is 0. Take minus 2 to the right side. 2y will be equal to 2. Then divide by 2 by 2, you get your y is equals to 1. So the value of y in that matrix is 1. So that the value, the determinant becomes 0. So that is the case for inverse of a matrix, where they have mentioned the aspect of no inverse to imply they are singular matrices. The last case, last example, before we can conclude our lesson, you are told to find the inverse of the matrix. Find the inverse of the matrix 8, negative 4, negative 7, 3. You find the inverse of the matrix 8, negative 7, 3, negative 4. The students should now be able to tell the elements in the leading diagonal, it's 8 and negative 4. The other diagonal is 3 and negative 7. Therefore, our determinant will be equal to 8 times negative 4 minus 3 times negative 7. Minus 3 times negative 7. 8 times negative 4, we have this as negative 32, minus 3 times negative 7, negative 21. Negative, that turns to positive, and therefore this is negative 31. So this is negative 11, negative 11. Then we get to the inverse. With the inverse, we are saying we interchange the elements in the leading diagonal. So negative 4 takes that position. 8 takes what is negative 4. Change the signs. So that is 7, negative 3. And then multiply by negative 1 over 11, or negative 1 over the determinant. By expansion, negative 1 over 11 times negative 4 gives us 4 over 11. Negative 1 over 11 times 7 gives us negative 7 over 11. Negative 1 over 11 times negative 3 gives us 3 over 11. And negative 1 over 11 times 8 gives us negative 8 over 11. This is the inverse of our matrix. That is the inverse of our matrix. Therefore, students, we have discussed 3 items in our lesson. We've discussed the determinant of a matrix, the inverse of a matrix, and we've joined those two using what we call a singular matrix. And we've said a singular matrix, a matrix whose determinant is 0 or it has no inverse. So this is your practice questions in what we've been able to discuss in our lesson today. So this is a practice of study questions. Number 1, you are told to find the determinant. Find the determinant of the matrix T, which is 1, 8, negative 2, 7. Q, the matrix Q has negative 8, negative 5, 10, negative 12. You find the determinant of those two matrices. Number 2, this is what you'll attempt. Given that M is equals to 2, 9, negative 1, 4. N is equals to negative 1, negative 7, 3, negative 6. Find part A. Find part A, the matrix P such that P is equals to 3n plus 2m. 3n plus 2m. Part B, you find the inverse of P. You find the inverse of P. And number 3, students, this will be your work again. You are told, given that Q is a matrix 7, 7, 8, 7, 2x plus 4. Given that the matrix here is singular, find the value of x. Find the value of x. Find the value of x. And lastly, number 4, find the value of m for which the matrix m less 7, 8, 10, negative 4 has no inverse. For which the matrix M less 7, 8, 10, negative 4 has no inverse. Those are your practice questions that you'll be able to look at after we are done with our lesson. So in brief, we've been able to look at 3 items again: determinant, inverse, and then singular matrices. So that is all for our lesson today. We stop there until we meet in our next lesson. I've been your teacher, Mr. Ndenga. Help us.